This is a production of Cornell University.
How does that heat actually move through the soil? Okay, we've got the surface of the soil, we shine light on it, the sunlight, it heats it up. Okay, we understand why it heats up. Well, how does that actually heat get transferred? Okay, all right. This conduction is basically based on what we call the Fourier's equation or Fourier's law. Okay, and this is the equation down here, but let's explain the equation by actually looking at a block. Okay, here's a material, okay, and it's getting heated up this way. Okay, how effective this thing is to transferring the heat basically is a measurement of how conductive that material is, the effectiveness of that heat to conduct, the area that's actually conducting, okay, how big is this object, and how much surface area this object has with the object that it is heating up, okay, and the driving force, i.e. the gradient. If this is cold on this side and hot on this side versus hot on this side and hot on this side, you can certainly imagine the conductance is going to be a lot slower in the hot versus hot system versus the hot versus cold system. Okay? That law is the amount of heat crossing a certain area in time. Okay? So heat flow, we measure it as a Q, but basically it is a measurement of change in heat over time. Okay? A is the cross-sectional area. That's the area that this is moving through. Okay? K is the conductivity, how effective it is as a heat conductor over a change in time, over a change in distance. Okay? Questions? K is the thing that we really should be concerned about right now. Okay? We can understand if I have a temperature gradient, that makes sense. And we can certainly imagine that to contact, the size of the object is going to have a huge impact. Okay? But let's think about how fast this object can actually conduct that heat. Okay? And it really depends on the soil's water content. This is a particle, an individual solid mineral. Okay? The heat moving from the top through the object, it's pretty fast. Nice contact points, pretty consistent material, moves through. Okay? The same volume of material, but you actually have individual particles. You'll note that the transfer points are just where those two pieces are touching each other. So I am limiting the flow of energy, or the flow of heat. This system, the system is not limited by contact points. The whole thing is a contact point. This one, the same volume, I have very limited transfer. Okay, now with a soil system, yes, we have solid particles, but we're generally talking about lots of little particles in a volume. Now, let's take that same system that we have here and we add water to it. Well, what happens? The water now is a player. The water now can conduct. The contact points have dramatically increased. Okay? The water moves through and transfers that water, or transfers that heat. Okay? Now, if we actually look at the particles themselves, this basically means that sand is the best, clay is in the middle, peat is the worst for conducting this energy. Now, think about this. Why? Why would we think that? Sand versus clay versus peat. Certainly the sand and clay we can sort of imagine over the peat. Well, why? Why is it better in peat? The solid mineral materials. Let's look at our volume. I got one volume. I start packing it up. Do you want to say something? No? Go ahead. If I have a given volume and I fill it with sand versus peat, which of these is going to have more contact points to transfer that energy? The sand will. And hopefully you guys have all picked up peat. You see how light it is, how much pore space is in there? Okay? And that, in essence, is what they're talking about here. How much contact, how much material is actually conducting this material, conducting the heat. Here's a couple of examples here. We're basically looking at quartz versus dry sand versus wet sand versus water versus air. Quartz, really high conductance. Have you guys been on the beach in the summertime, under the sun? What do your feet feel like? They're pretty hot. Okay, they're conducting that heat to the bottom of your feet. Okay, what happens when you get into the wet sand? Cools down. It's still pretty good at conducting that heat, but not as good as that packed sand around you. Okay, water versus air. The interesting thing here, if you note, is that if we went back and took a look at the thermal capacity of water is pretty high compared to solid material, but the thermal conductivity of water compared to solid material is a lot lower. Okay, of course it's a lot higher than air. Okay, so let's put these two together. We have thermal capacity and heat capacity. Basically, the combination of the two of them determine the shape of the temperature curves, or the thermal temperature profiles through a soil. Okay, so here's temperature, and this is time, noon, noon, noon. This line right here represents 25 centimeters down. This line right here represents 1 centimeter. Okay? Now, I've posed two questions here. The first is, when will heat flow be most rapid? And the next one is, where will heat flow be most rapid? Same location in essence, and time. They basically correspond to each other. Okay, if I'm moving from high temperatures to low temperature, you certainly should look for the high points temperature-wise, and then look for the cool points, because that's where the energy is going to be transferring. Okay, so let's imagine this one, noon at 1 centimeter. Where's the heat moving? Some of it's going to be coming back off, but where's the heat moving? It's going to be moving downward, right? Dramatic, well, relative to this profile, the dramatic delta in the temperatures is right here. Okay? This material is heating that below. Below is heating up, but look where its hottest point is. At midnight. 1 centimeter, its coolest point is at midnight. What's going to be, where's the temperature going to be going now? It's going to be going from 25 centimeters down to 1 centimeter. Or up to 1 centimeter, basically, I should say. Okay, does that make sense? So we've literally inverted the heat profile just because we've changed the temperature at the surface. Well, what's happening at the surface? At noon, the sun's shining. At midnight, the Earth is re-radiating and getting rid of all that temperature. Does that make sense? Questions? So the when is here. The where is here. Does that make sense? Let's keep going. Okay? This is out of your book, and basically what you're looking at here is temperature in Celsius going up here, and the months of the year. You have a variety of different different temp depths here. You have basically 7.5 centimeters, 30 centimeters, and 90 centimeters. The black dot here basically represents the air. The black dot, that line, basically represents the air temperature. Okay? Air temperature, January, December, pretty cold. July, June, July, August, warm. Okay? We can see that reflected on the soil surface, which is the 7.5, this dark solid line. It basically mimics the air temperature. But you'll note that the 30 centimeters and 90 centimeters, the peak is here, the peak is here, the peak is here. So what's happening? The heat is being transferred down, but it takes a while for that profile to get transferred down. So it's delayed. Okay? And then, someplace down in here, in September, October, we have an inversion. Okay? The surface temperature is matching that air temperature and dropping. The peaks are starting to drop down because they're starting to transfer their heat back up to the surface. But even in December, yes, they've gotten a lot colder, but even in December, they're fairly warm, certainly relative to the air temperature and the surface. So a seasonal change. Okay, here this one so far we've seen is a daily change. Now we're starting to see seasonal changes. Okay, now how about we look at that through the whole year and we basically look at those curves. Okay, here's the soil surface down to 300 centimeters, 3 meters. Okay, you can basically look at these curves. We'll start in January, cold surfaces, warmer subsurface. January, then we get March, sun starts coming out. Okay, that's the season of mud around here, right? Starts warming up at the surface, but you'll notice that the soil is actually getting colder down here. The heat's still being transferred up, so it's getting cooler. March, May, right here, more sunlight coming in. Sunlight, the energy is starting to be transferred down. You see at this point, we're looking almost like a straight line up and down. Yeah, there's still a little bit more energy going upward, but once we get to this point, you can see the energy starting to go down, and that's why the temperature starts coming up. Okay, May, July, really hot. Energy transfer here and here, all heating everything up. It's hot here, transferring it down, moving it forward this way. Okay, May, June, July, and then we start having September. Okay, surface starts cooling down, bottom is still heating up. Okay, this is still colder than that, so there's certainly energy being transferred down. September, November, right here, this line right here, we start seeing the top getting really cold, energy is being transferred from below to up. And so as a result, we start seeing this march back down, and we'll ultimately get right back to January. Does that make sense? We have heat moving downward when the surface is hot. We have heat moving upward when the surface is cold. All right, it's not just about seasonality, it's also about management. Okay, here is basically soil temperatures in a clear cut. Here's soil depth, surface to 28 inches. You're basically looking harvested and bedded versus an uncut forest. Wait a minute, no, I did that wrong. This is the uncut forest. This is the harvested and bedded, and this is the clear cut. Yes. Yes, okay. So, uncut forest, soil depth, cool soils compared to a harvested and bedded. Basically, this means it's not only has it been harvested, but everything's been stripped out. So all the recut material, all the scrap stuff, it's been taken out. Okay? So just look at the comparison of these two. Well, what's going on? This is not a seasonal thing. This is a management effect. What's the management effect? If I've taken the trees out and I've taken all the cover out, I've got a lot more energy actually hitting the soil. And if I got more energy hitting the soil, it's going to heat it up even more, and we're going to see that transfer moving down. Make sense? So a management effect. How about a much even more dramatic management effect? Let's talk about mulching. Okay? Classic example here. We've got the temperature, basically the 0 point here, versus negative versus positive, versus a bare soil. This soil has a leaf mulch in it. Air temperature, soil temperature. This line right here represents the temperature line. Okay, and you'll note that at depth, they're basically the same, and at the surface, the air temperature is the same. The change is really in here. Well, what's going on? This one, in fact, has snow on the surface. This one doesn't. Well, look at where the temperature line hits the surface here. In this case, right here, it's at 1 degrees. In this case, when it hits the surface, it's at -1. Well, what's happening? This surface is definitely warmer than this surface. So what direction is the heat going? It's going up, all right? So it hits here, and it's hitting here at 1 degree Celsius because the heat's being transferred up here. Certainly you could make the argument that this soil is going to cool down a lot faster, okay? Because it's 1 degree, the snow melts, and I don't have any snow there. What's happening here, though? When it hits the surface, it's not at 1 degree, it's at 3 degrees. The energy there is then being transferred to this mulch zone, these leaves. And this is where thermal conductance comes into play. This is like a peat versus a mineral. The leaves, there's a lot of air in here. There's a lot of pores. It doesn't take a lot of energy to heat up the air, but that air doesn't conduct it very well. And the surfaces of the leaves that are touching each other, they're very limited. So the transfer of heat through the leaves is very, very slow. And so as a result, this zone in here, look at the change in temperature here versus the change in temperature here. This is basically acting like a blanket. Warm body down here, cool air up here. The blanket serves to keep the insulation or slowing that transfer of hot air out of the system. Cool?
This has been a production of Cornell University, on the web at cornell.edu.